In this video, we're going to talk about the rocFFT library, which performs fast Fourier transform. So fast Fourier transform, or Fourier transform, is performing a series of operations that is expressed by the equations as shown in the slide. Here in this video, we don't want to talk too much about the equation, but I want to show you the complexity of regular discrete Fourier transform operation is represented by big O(n) square. So if you look at the first equation, this is one-dimensional discrete Fourier transform. The inner loop is represented by this summation sign, and the outer loop is represented by this 4 representation. So that is why we have O(n) square. It is also true for two-dimensional discrete Fourier transform. Fast discrete Fourier transform is a theoretic implementation that can reduce the complexity from O(n) square to O(n) log n, which can reduce a lot of operations and make the computation much faster. Why is fast Fourier transform so important? Because we need to perform signal processing in many different domains. For example, in this figure, we can see the original Lana image. If we perform a Fourier transform, we can get a figure that looks like this. This is not human interpretable, but it contains exactly the same information as the original Lana image. And what this figure represents is the strength of the signal at different frequencies. The closer to the center, the lower the frequency, and the closer to the edge of this figure, the higher the frequency. If we remove the low frequency signal, we can get this type of figure. You can see we can extract the edges of this figure and remove the big and flat area. But if we only keep the center of this image, we blur this image by removing the edges. FFT is commonly used in image processing process because in one way we can use FFT to implement image convolution. So for example, in this image, we want to use convolution to detect some features of this brain tumor. And the FFT can convert a convolutional operation into a multiplication operation, which can significantly reduce the computational complexity. That's why FFT is so important as a building block of more complex algorithms. So now we understand the importance of the FFT algorithms. Let's look at the rocFFT APIs. Still, we're going to use one example to show how to use rocFFT. So at the beginning of this program, we need to call rocFFT setup. It initializes the environment. Then we perform some initialization work, and this is regular heap program. We first define n as the number of samples in the signal that we want to process. Then we need to allocate a heap device buffer, which just simply use heap malloc API. As you can see here, we assume each data sample is a complex number, and we use a float tool to represent a complex number, where this x represents the real part of this complex number, and this y represents the imaginary part of this complex number. Then we copy the data to the device, using the regular heap API. Before we perform a rocFFT operation, we need to create a plan. We start with defining this plan as a null pointer, then we use this rocFFT plan creator API to create this plan. We need to tell rocFFT about how we want the operation to be performed. For example, we see this rocFFT placement in place argument, which represents we want to reuse the input buffer to store the output data. And then we see this rocFFT transform type complex forward, which represents two pieces of information. That this data is complex data, and we want to perform a forward faster Fourier transform rather than the backward faster Fourier transform. Now we have this precision single, which represents what's the data type we want to use. And the rest of the arguments represents more information about our input data, including the dimension and the length of the data. The rocFFT documentation has more information about the arguments here, so users can refer to the documentation for more information. So rocFFT plan tells rocFFT library about what we want to do next. And rocFFT can decide the actions that we want to take. We want to create some buffers for the rocFFT to use. And we don't really know what's the buffer size. But since the rocFFT plan is there, and rocFFT knows what's going to happen, it can tell us what's the buffer size. So as you can see in the second line of the code, rocFFT plan get to work buffer size. We can get a buffer size that we need to allocate. So rocFFT can tell us the buffer size, and we can allocate the buffer in work buffer. Then in this if statement, we'll allocate this buffer in the second line using the HIP malloc API. We also need to create this rocFFT execution information data structure, which includes the information that we want rocFFT to use for the next execution. At this point, we have all the information we need for this rocFFT to execute. Now we can call this rocFFT execute to execute the plan. We provide a plan, we provide the information, and we provide the input buffer, and also the output buffer. And here this output buffer is non-pointer because we want to reuse the input buffer. And also this rocFFT execute is an asynchronous operation. It doesn't guarantee that the GPU completes the execution before this function to return. So if we want to make sure this execution is completed, we have to use a heap device synchronize to explicitly synchronize between the CPU and the GPU. Finally, we clean up the execution environment, we free the buffer, we remove the information for execution, and we destroy the plan. We also call an rocFFT cleanup to free up the environment. As you can see in this example, rocFFT is not a very complex library. So it basically follows a few steps. At the beginning, you create a plan. Then you provide the information for the execution. In the third step, you make the execution happen by calling this rocFFT execute function. And finally, in the fourth step, you free up all the resources. That is a common pattern that you would use rocFFT library.